What if Noah's Ark wasn't just a legend, but a calculated project, millennia before modern engineering? Today, we follow clues of proportions, materials, and winds that suggest knowledge far beyond what we'd expect. Before we open this structure like a living technical blueprint, like the video, subscribe to the channel, and come see how faith and calculation can fit in the same hull. Heavy rain falls on cracked ground. Thunder makes the sky vibrate as drops hit wood. In the background, the echo of hammers, as if, millennia ago, someone were still building something colossal. For centuries, Noah's Ark was read as metaphor, but recently, the debate left pulpits and entered laboratories. Engineers, physicists, and naval designers have once again approached Genesis as a technical notebook. What if the instructions given to Noah hide engineering principles far ahead of their time? This documentary starts from that hypothesis and confronts the ancient account with scientific studies, computer simulations, and structural analyses from research centers. The investigation crosses the slopes of Mount Ararat, where some see indications, fossilized wood, traces in rock, and moves on to labs that test scale models in wind tunnels and wave tanks. The results impress. Dimensions, proportions, and solutions described in Genesis prove plausible, suggesting practical command of hydrodynamics, buoyancy, and stability. How could a society without electricity, cranes, computers, or precision metallurgy execute something so ambitious? And why build a ship far from the sea? Throughout the chapters, we dismantle the puzzle: proportions and stability. Materials, including the enigmatic gopher wood and bitumen for waterproofing. Viable construction methods without modern technology. The geographic paradox of building inland. The internal plan. 3 levels: compartments, circulation, ventilation. Logistics for thousands of animals. Food, water, and sanitation. And finally, the structure's resilience under outlier storms. When science and the Bible meet, the impossible becomes an engineering problem. Hypothesis, simulation, test. The goal isn't to arbitrate faith, but to measure coherence, where the text converses with physics and where pieces are missing. Prepare to see this story under a technical experimental light, step by step, as on a job site, seeking a direct answer to an ancient, bold question. How could Noah's Ark have been built? Throughout history, we've looked to the sky for answers. Sometimes they're in the numbers. 3 measurements from a millennia-old manuscript may hide one of the most advanced projects of the ancient world. Genesis assigns the Ark 300 cubits in length, 50 in width, and 30 in height, roughly 137, 23, 14 millimeters. On a modern scale that rivals large ships, longer than a soccer field, wider than many public buildings, and as tall as a 4-story structure. What stands out most, however, is the proportion. The 6:1 ratio, length-width, is a classic for stability on the open sea. It's not for speed or fine maneuvering, it's for not capsizing under severe waves. Curiously, builders of the 18th and 19th centuries only consolidated something like this after much trial and error, while the biblical text suggests the solution millennia earlier. Ancestral intuition, practical tradition, well-followed instruction, whatever the explanation, the numbers don't look random. And that intrigues engineers. Simulations and comparative tests reinforce it. Geometries close to the Ark's show excellent stability against roll and loss of center of gravity. The elongated rectangular form, though unusual for high-performance ships, behaves like an optimized barge. It rocks, but is hard to overturn. Why? Because stability is the heart of the problem. In heavy seas, the priority isn't to cut through waves. It's to maintain attitude and protect those on board. A 61 vessel distributes mass and buoyancy so as to resist lateral forces without the restoring moment being overcome. The height of 30 cubits, 114, isn't a detail. It gives volume for 3 decks, which affects logistics, storage, circulation, segregation of species, and structure. Each deck acts as a diaphragm, reducing bending and torsion along the hull. The width of 50 cubits, 823 bilauds, favors a low center of gravity and load distribution. Pillars of passive safety. Historical comparison sharpens the view. The wooden ship Wyoming, out of 107-meter USA, required pumps running continuously because of hull deformation. Wood works over long spans. It warps, yields, opens gaps. The compartmentation described for the ARK would function as internal bracing, a kind of skeleton containing longitudinal bending and shear, reasoning that naval engineering would later systematize with rigid bulkheads to mitigate flooding and load variation. In short, the measurements, proportions, and arrangements in Genesis form a technically defensible set for the stated objective. Not to sail fast, but to survive. The rest of the investigation addresses materials, construction methods, ventilation, sanitation, biological logistics, and performance in extreme storms, building, with data, the bridge between the ancient account and modern engineering. Another crucial point, the ARK didn't need to navigate in the modern sense. There's no mention of rudder, sails, or propulsion. Its purpose was to survive, to float safely for a prolonged period. That change of objective alters the design. It forgoes hydrodynamic gains, speed, maneuvering, to maximize robustness. In that regime, the biblical dimensions leave poetry and enter functionality. One might object, but how could a man without formal calculations and without computer models produce something so accurate? Some see divine inspiration. Others propose accumulated experience from building barges and rafts on rivers, passed down through oral tradition. A third path, empirical observation, smaller prototypes, trial and error, until a set of proportions imposes itself by performance. If it were pure fiction, we'd expect whimsical measurements, at odds with physical principles. We see the opposite. Numbers that dialogue with buoyancy, transverse longitudinal stability, and wave resistance. In tank models, ARK-like hulls exhibit gentle behavior under irregular seas. They tend to orient with currents, dissipating energy without accumulating dangerous momentum. The geometry also converses with internal operations. With 3 levels, it's possible to isolate larger animals on the lower deck, lowering the center of mass, dedicate the middle to stores, silos, and distribution channels, and reserve the upper for birds, small animals, and the crew, closer to light and ventilation. It's an arrangement that, besides being logical, reinforces the hull from within, as if each slab helped tie the walls together. From the standpoint of external impacts, the broad, relatively flat bottom acts like a shock absorber against debris and cross seas. Unlike a fine hull, great for cutting water but capable of absorbing dangerous energy, the elongated box spreads stresses over a larger surface, reducing peak tension. In other words, the ARK sacrifices performance to gain resilience. The great challenge of long wooden spans is inevitable. Creaking, gaps, flexure. That's where partitions and transverse reinforcements come in. The rooms in the text, read technically as stalls and bulkheads, create modules that limit deformations, contain crack propagation, and, crucially, shorten the path of infiltration if a joint fails. It's the difference between localized damage and collapse. When universities, naval centers, and museums build scale replicas, the verdict converges. It floats, it's stable, and it weathers storms that would topple less robust hulls. That doesn't prove the historical event, but it supports the project's plausibility. The question remains, was Noah merely executing a detailed plan, or a craftsman who, without formal math, grasped engineering principles? The answer may be unreachable, but the preserved numbers produce a drawing coherent with the physics of the sea and suggest the subtle lesson that a fable can carry enduring technical parameters. The riddle of gopher wood has puzzled for centuries. The term appears only once, and its exact meaning is disputed. The order is clear. Make an ark of gopher wood, but gopher, has no secure parallel. Species, group, or technique. Common hypotheses: cypress, cedar, yew, and acacia. Woods with good moisture resistance, mechanical strength, and workability with simple tools. Some propose a species now unknown, or that gopher designates dressed processed wood. A process, not a tree. Materials science helps filter. To support weight, hydrostatic pressure, and harsh climate, the material needs high specific strength, low water absorption, tolerance to torsion and bending, dimensional stability after curing, and joints correctly oriented to the grain. Modern tests show strong performance from Mediterranean cypress, yew, and acacia even without additives, provided there's slow drying, cuts along the grain, and well-designed joints. Another key point is waterproofing. Mesopotamian peoples mastered bitumen for sealing and caulking long before iron became widespread. Genesis commands coating inside and out. From a naval standpoint, that's a leap. Caulking seals gaps, reduces gas exchange, and, combined with vegetal fibers, becomes an effective composite, a water barrier with slight damping. If gopher is process plus sealing, the mystery shrinks. The question becomes how to prepare wood for the sea, not which tree to use. Then comes the tool dilemma. Before iron was common, the arsenal was stone and early bronze. Simple saws, adzes, chisels, gouges, rudimentary planes. Even so, ancient cultures achieved precise geometry with joinery. Tenon and mortise, half-lap, dovetail, wedges, and fiber lashings, linen, reed, vegetal ropes. It recalls traditional Japanese carpentry, structures without nails, where the joint lives with the wood, flexing without breaking, an essential virtue in a hull that works with water. It's possible gopher meant a functional set, one species for framing, ribs, stringers, another for planking, another for interiors, stalls, decks. The mixed wood logic used to this day, exploiting each property in the right place. As for weight, an ARK Mara 137 m long with dense structure and live cargo could exceed 20,000 tons. That isn't absurd when we recall that buoyancy depends on displaced volume and distribution. The equation demands woods with good strength-to-weight ratio, controlled porosity, and assembly that minimizes gaps. Mistakes of species, grain orientation, or assembly would be catastrophic, and yet the account says it floated for months. The triad suitable wood plus bitumen plus compartmentation closes the circuit. Bulkheads and stalls act like diaphragms, cutting longitudinal bending and shear on long spans, exactly what naval engineering would later systematize. This internal architecture helps the outer skin, hindering cracks and deformations. Without nails, viable. So long as there's joint design, Linen, hemp ropes, braided reeds, wedges, and hardened wooden locks tie long panels. Bitumen acts as a natural glue, completing watertightness. The set delivers stiffness where needed and flexibility where healthy. Precisely the balance that keeps a hull alive and tough. In computational models, researchers simulated chronic humidity, pressure, and thermal cycling on panels and frames. The results support the plausibility of an ARK adrift for months without catastrophic performance loss, provided the wood is properly prepared and sealed. That doesn't prove the historical event, but it corroborates the technical design. And the traces? Carbonized wood fragments around Ararat have been C14 dated across millennia. Direct identification with the ARK is controversial, but such finds keep the investigative window open. Meanwhile, the real riddle persists where it matters. How did someone, before formal naval engineering, know what to choose and how to treat it? Perhaps the answer lies in the sum of observation, artisanal tradition, and practical experiment. The university of those who build with their hands. The fact is, wrong choices would sink everything. The account, however, describes a mission accomplished. Modern woods often rely on chemical treatments, metal reinforcements, and varnishes. If the ARK was as described, it survived with wood, bitumen, and design. Three words that, together, still sustain large works. Searches continue, and so does the debate. At the heart of this story remains a question that challenges our modern self-confidence. How did they know which wood to use before naval engineering existed? If this dive into biblical engineering is surprising you, drop a like and stay to the end. What comes next questions much of what we imagined about the flood. Raising a structure over 130 meters long, nearly 14 meters high, and over 20 meters wide by sheer manpower. No cranes, no engines, no forged steel. Only simple tools, coordination, and a stubbornness that spans decades. At first glance, it sounds impossible, till we remember how ancient civilizations moved monoliths and giant logs. The biblical account doesn't summon an empire, a city-state, or an army of workers. It calls a family. That creates the central logistical dilemma. How does such a small nucleus handle something so colossal? Excavations and studies on ancient techniques show that even for adobe houses and stone structures, the workforce was usually numerous. Hoisting blocks, transporting logs, assembling frames. Everything demands planning and synchronicity. And, according to the text, Noah had neither social prestige nor a support network. The answer comes from experimental methods replicated by engineers and historians. You can do a lot with little when you use good levers, ramps, rollers, and pulleys. To move 10-meter timbers weighing hundreds of kilos, the combo earth ramp plus log rollers, P plus hemp ropes, reduces friction and vertical effort. By alternating rollers ahead and retrieving those behind, you create a belt that advances slowly, but safely. Experiments in Japan, Egypt, and South America have demonstrated transport of up to 1 ton using only human power, as long as counterweights, supports, and team rhythm are respected. To lift pieces several meters high, enter block and tackle families and compound pulleys. Each loop of rope multiplies force, and modular wooden towers act as scaffolding. If the ARK has 3 levels, it's reasonable to suppose temporary platforms, demountable towers, and braces that advance as the work grows. In modern reconstructions, like the famous installation in Kentucky, heavy machinery was used, but pre-industrial principles suffice. With time, cadence, and method, the task moves. Joinery is the most elegant technical secret. Without abundant metal nails, the structure relies on joints. Mortise and tenon, dovetail, half-lap, scarf joints, and wedges. These living unions allow microflexion without rupture. Exactly the desired behavior in a hull that works with the waves. Fiber lashings and locks complete the package. And bitumen is not just for sealing. It works as a natural binder along contact lines, filling micro-voids and improving tightness. The construction sequence proposed by 3D simulations tends to be 1. Keel, the longitudinal axis, the spine of the hull. 2. Frames, transverse ribs, and stringers. 3. Horizontal bracing that later becomes decks. 4. Outer planking and caulking. 5. Internal compartmentation, stalls, rooms. 6. Systems, gutters, troughs, cisterns, louvers, vents. Building from the center toward the ends and from bottom to top gives progressive self-stability. Each finished phase supports the next. This allows effort to be segmented. The family finishes a module before advancing, keeping the structure tied the whole time. How long would it take? Technical estimates, considering 6 to 8 people, basic tools, and continuous shifts, range between 55 and 75 years. That interval matches the long window between the flood warning and the onset of rain in the account itself, which at least resolves the time versus method equation. Technically, we're talking about a project of extreme logistics. Meticulous planning, material management, drying, cutting, reserving, disciplined task repetition, and human endurance. It's a job site that runs on process, not improvisation. Faith may be the fuel. What raises each plank is precision. Choosing the right grain, nailing the joint angle, locking the fit, caulking the seam. Comparing with modern construction misleads. Today, buildings require hundreds of people. Cranes, BIM, concrete, and steel. And that makes it seem unlikely that a family could raise a wooden colossus. But broken into phases, the difficulty becomes patience and method, not physical impossibility. One advantage of the project: the ARK didn't need to navigate or be fast, only float safely. That allows simple lines and a focus on robustness. Less aerodynamics, more stability, straighter planes, heavy stringers and braces. Safety is born of compartmentation. Bulkheads confine damage if a joint opens. Decks act as diaphragms, reducing deflection. Bitumen accommodates expansion and ensures tightness. In replicas with limited tools, research groups converge. Difficult, yet possible. With possible on the table, the discussion leaves mechanical improbability and moves to time, method, material, and discipline. The ARK becomes a process manual. Levers and pulleys instead of engines, geometry instead of software, compartments instead of steel, bitumen instead of resin. Not improvisation, technical persistence. Final proof? Perhaps never. But summing ancient transport, joinery carpentry, sealing, and assembly sequence, the picture is clear, feasible, and worthy of respect as an intelligent pre-manual solution. A ship without a sea, a giant structure on dry ground, a nautical project in a mountainous region with no outlet to the ocean. Why raise a colossal hull far from water? The most cited region is Ararat, eastern Turkey, far from the Mediterranean and the Black Sea. In today's engineering light, it sounds costly and unnecessary. But the narrative inverts shipyard logic. You don't build to take it to the sea. You build for the sea to come. Transport the Ark to a river? Unworkable. Load estimates and simulations show that moving 20,000 tons without wheels, rails, or machines is impractical. The coherent plan is to prepare the hull and wait for the water event. In project language, extreme scenario requirement. If everything will be covered, you build where it's safest and wait. Geology offers a plausible frame. Prolonged rains, tectonic movement, and aquifer ruptures can raise waters to high valleys, echoing the ancient text of fountains of the deep and windows of heaven. In that scenario, building on solid ground stops being strange and becomes strategic. No tides, no coastal erosion, no salinity accelerating degradation, and less risk of attacks. At elevation, the site gains a stable base, less humidity, and more predictability. There's also a logistical gain. Curing wood, dressing planks, caulking, all take time. On the coast, salt and fluctuating humidity hinder curing. In the mountainous interior, drier air and more stable temperatures optimize drying and preparation, ideal when building something huge with little manpower. Bonus: far from centers, there are fewer intruders and room for staged tests. Sector water tightness, compartment trials, checking vents and gutters. In risk management, the trade-off makes sense. Forsake the ease of launching to sea for job site robustness, like assembling a rescue craft in a safe hangar and only starting the engines when the environment demands it. Topographic models on Ararat map basins that can fill rapidly under extreme precipitation. Even if the flood's scale is debated, one functional point remains. No one invests decades in such a hull without purpose. It only makes sense if one believes in a radical environmental change. Building away from the coast also frees the schedule. No tidal windows or port pressure. The rhythm is set by the process, not the clock. Each joint, each lock, each layer of bitumen goes in at the right time. When the water arrives, everything has to be ready. Cisterns, troughs, drains, vents, stalls, and passages already tested. The initial "it makes no sense" becomes "it makes perfect operational sense." Building where there's no water is embarking without hurry and without interference, and the water event will provide the launch. Which brings us to the interior. Floating isn't enough. Life must be sustained. From the outside, it looks like a box. Inside, it's a system. 3 levels, compartments, corridors, ventilation points, and functional areas for months of operation. 3 decks aren't just space optimization. Each deck is a rigid diaphragm tying walls, distributing forces, reducing flexure, and increasing inertia. Vital in very long hulls. Volumetric modeling at traditional dimensions estimates 50,000 Theater-3 of usable volume. Enough for thousands of animals, tons of provisions, reservoirs, service corridors, rest zones, and sanitation areas, without becoming a chaotic maze. How to distribute it all? Researchers propose a layered organization. Lower level, large, slower metabolism animals. Keeping them close to the bottom lowers the center of gravity, increasing stability. Stalls here can be more robust, with sloped floors and lateral drains for liquids. Middle level, medium animals, silos and food stores, cisterns, and gravity-fed distribution channels. It's the Ark's logistical heart, where weight and access need balance. Upper level, birds, small animals, and humans. Proximity to the Tsohar, the continuous upper opening per many readings, improves natural light and ventilation, essential for routine, hygiene, and well-being. Compartmentation, called rooms in the account, serves multiple roles. It works as a behavioral barrier, prevents escapes and conflicts, as a structural element, acts like bulkheads, locking forces, and as sanitary control, limits the spread of odors, gases, and aerosols. In modern terms, it resembles the layout of livestock barges and stables designed for one-way flow: entry, feeding, cleaning, exit. Internal circulation must be fluid. Longitudinal corridors, a central spine or two along the sides, with transverse crossings at regular points, let the crew feed, remove waste, inspect, and maintain without crossing stalls. Hatches and simple lock grates speed up routine and reduce risk. As for impact resistance, the ARK, broad and relatively flat-bottomed, behaves like a reinforced barge. It spreads debris impacts and distributes loads over a larger area. Inside, decks and partitions turn the box into a three-dimensional truss that crumples less at localized points. If one sector is damaged, bulkheads confine the breach, reducing the chance of cascading failure. The environment must be breathable. The mention of the Tsohar suggests a passive ventilation solution via stack effect. Hot air rises and escapes through the upper opening. Fresh air enters through controlled gaps and lower vents. With well-distributed compartments, ventilation spreads, and ammonia and CO2 are mitigated. Curtains, louvers, and angled flaps prevent water ingress even with headwinds. Another pillar is water management. Channels and gutters feed troughs by gravity, connected to cisterns that ideally collect rain through the Tsohar itself, with diverters to rudimentary filters. Internally, that means calculated slopes and locks to prevent water from sloshing with the roll. Refill is simple. Open internal gates, drain, clean, close. Cleaning benefits from slightly sloped floors, collector trays under raised stalls, and waste routes that don't cross feeding areas. Composting, layers of straw and wood shavings, and the use of ash help dry, reduce odors, and inactivate pathogens. All this must be in the design. Improvising after departure would be reckless. From the human perspective, the upper level favors light, routine, and mental health. In long confinements, think submarines or space stations, clear cycles of work, meals, and rest reduce stress and error. Well-organized storage, accessible tools, work benches, basic carpentry, repairs, and observation posts by openings create an operational kitchen for 8 people. From the animal perspective, predictability is key. Feeding at regular hours, low light in rest areas, visual barriers to reduce stimuli, and, when possible, juveniles instead of adults, as they need less space and food. All of that converses with the layout. Bigger stalls for large herbivores, suspended crates for birds, nests and perches up high, cabinets and simple gravity feeders. Weight control and load balance are continuous. As food and water are consumed, the center of gravity migrates. The internal plan foresees shifting bales between stalls and stores to keep the ARK trimmed, avoiding dangerous lists. Floor markings, tie-down points, and rudimentary balance scales help the crew correct asymmetries. What about emergencies? The layout needs redundant routes. If one corridor is blocked, another reaches the same destination. Latches that open from inside, doors that don't jam with swelling, stair risers low enough for carrying loads, details that seem small, but save time when the roll increases. Although it sounds sophisticated, none of this requires electrical technology. The ARK is essentially an example of passive engineering. Gravity for water and food, convection for air, compartmentation for structure and behavior, gutters and slopes for cleaning, What ties it all is the internal plan, the map that makes the box function as an organism. Ultimately, what emerges is system coherence. The Ark wasn't designed to conquer the sea, it was conceived to survive it. Every deck, every stall, every span serves that mandate. Seen this way, the interior stops being improvisation and becomes design. A floating fortress, a preservation chamber, an isolated habitat that, for months, would keep what lived on Earth pulsing. Modern parallels, space stations, submarines, self-sufficient shelters reinforce the impression. Sustaining life without external connection is a challenge of flows, stocks, and waste. The Ark anticipates this reasoning with wood, rope, and bitumen. If the outside was just a box, the inside was a survival machine. The compartments, therefore, weren't the end. They were the preparation. Soon, that ordered volume would be filled by thousands of creatures, all different, all demanding in their own way. The internal plan was the board. The pieces still had to be placed. Close your eyes for a moment and imagine the Ark's interior. Not empty spaces or absolute silence. The air vibrates. The enclosure pulses, breathes. There is movement, smells, rhythms. Thousands of creatures of different sizes and habits, confined in the same volume for over a year. How to organize that life without chaos, collapse, or losses? The clue lies in logistics and in a key expression from the account. According to their kinds. Here, kind doesn't equal species in the modern taxonomic sense. In Hebrew, the term min describes fundamental groups of living beings, not every variation within the group. That nuance changes the problem. If the goal was to represent basic kinds, it wasn't necessary to board all subspecies. One pair of canids, for example, could cover wolves, dogs, coyotes, as variations within the same kind. The reasoning repeats with felines, bovines, birds, and so on. Estimates from researchers aligned with creationist biology and population genetics suggest fewer than 1/400 terrestrial kinds with internal reproductive potential, doubled for male and female, and adding the clean animals, for which the text speaks of additional pairs, we reach about 7,000 to 8,000 individuals. That seems like a lot, until we compare it with the Ark's usable volume. With more than 50,000 audacious available and prioritizing juveniles, smaller, lighter, and with lower energy demand, occupancy would not exceed a fraction of the space, leaving margin for food, water, service corridors, tools, and rest areas. The crucial question, however, isn't just how many, but how to arrange. Contemporary experience in livestock transport, wildlife management, and conservation centers points to 3 axes of success. 1. Segregate by habit and size. 2. Mitigate physiological stress. 3. Guarantee easy access to food, water, and cleaning. Hence, an intelligent geometry. Large herbivores on the lower level, near the bottom, reducing sharp movements since they sit near the center of gravity. Carnivores, likely fewer and with slower metabolism in inactivity, in isolated modules, with visual barriers and dedicated service routes. Birds and small animals on the upper level, taking advantage of light and airflow near the Zohar, upper opening, which facilitates hygiene and routine. There's also a behavioral trump card rarely remembered. They didn't need to be active. Under low light, predictable routine, and few stimuli, many vertebrates enter a torpor state, a metabolic economy similar to hibernation, even without extreme cold. That slashes per animal needs for space, water, and food, easing the upkeep of the whole. How to ensure precise allocation? The answer lies in preparation. The text suggests Noah received instructions in advance, which opens time to design stalls, size corridors, set feeder, drinker points, and plan separation of predators and prey. Another important detail, they will come to you. The selection, therefore, was not random. There was convergence, which allows route and lodging planning. Choosing juveniles is pragmatic. They adapt better to new environments, are less aggressive, require fewer resources, and, at the end of confinement, have more reproductive years ahead for recolonization. In wildlife logistics, that's classic. When possible, prioritize the young to reduce containment cost and risk. The mechanism then depends on space design according to behavior, deep stalls for large herbivores, quiet modules for carnivores, perches and nests for birds. Linear access for the crew, with pass-through hatches, simple locks, and corridors without blind spots. Layers, levels, and light used with intent, optimizing air control and routine. In practice, this echoes solutions used today in wildlife shelters, modern zoos, and rescue operations. One-way flow, low stimulation zones, easy cleaning, and constant monitoring. The goal isn't a display zoo, but a biological rescue capsule. Functional, safe, and predictable. Another key piece is conflict reduction. Wooden partitions or braided vegetal walls with openings that let the team see without being seen by the animals reduce stimuli between stalls and prevent panic. Sound control, less echo, fewer sharp noises, also lowers stress and reduces stereotyped behaviors. Contingency planning enters with it. Hospital stalls or quarantine areas, alternate circulation routes, and a basic manual immobilization kit, ropes, locks, movable barriers, complete the circuit. None of this requires electricity, just method. In the end, the logistical picture is that of a coherent system. The right animals at strategic ages, spaces designed for predictable behaviors, care routines that fit the number of people, separations that prevent accidents. That's why modern analyses consider the model viable and, in many points, efficient. What was there wasn't ornament. It was engineering applied to care. Each life occupied a thought-out place. And what meshes this mechanism isn't software. It's observation, field experience, and design. Yet this design only holds if the supply chain doesn't break. Keeping beings alive isn't only housing, it's feeding, hydrating, and cleaning. The ARK had to function like an organism with inputs, food and water, processing, the metabolism of thousands of creatures, and outputs, waste. And in a prolonged isolation scenario that requires simple, reliable, repeatable solutions. That's exactly where we go now: nutrition and survival. How to dose, preserve, and distribute the right food every day for thousands of mouths without electricity or industry. The answer runs through ancient techniques and intelligent use of gravity. Keeping thousands of animals alive for over a year is less a question of space and more a test of nutrition and process. Even today, with machinery and science, operating a conservation center at that scale is challenging. How then to feed such a diverse collection without electricity, refrigeration, or an industrial chain? The key lies in three old verbs: store, preserve, and distribute. Let's start with sizing. Considering around 7,000 animals, mostly juveniles, we have a daily consumption between 1.5 and 2 tons of plant foods, plus water. Over 370 days, that exceeds 600 tons. It sounds like a lot, and it is. But Given tens of thousands of cubic meters available and torpor-lowering energy expenditure, it becomes manageable with well-stacked inventory, access routes, and distribution points. How not to spoil so much food without fridges? Antiquity had answers. Sun-drying, dehydrating fruits, roots, grains, leaves, and hay reduces microbial activity and extends shelf life. Controlled fermentation, grains and forage in silos, even rudimentary, keep for months with natural acidification inhibiting pathogens. Sealed ceramic vessels, fired clay jars sealed with wax or bitumen protect honey, oils, legumes, and grains from moisture and pests. Plant packaging, large leaves, linen sacks, and baskets aid aeration and protect from direct light. Storing is half the job. Food must reach each stall every day, with few people and a predictable routine. Here, gravity enters as a silent motor. Elevated bins connected to wooden chutes or sloped ceramic tubes allow dosing by free fall. Pull a pin or open a small gate, and food drops into feeders. The principle is still used today in poultry houses and trough systems. For water, the logic is identical. Cisterns on the upper level, gutters, and drinkers per level. On rainy days, some water can be captured through the tsohar via internal gutters with simple filters, cloth, vegetal fiber, gravel. On dry days, consumption comes from reserves. The layout must prevent sloshing overflows, hence the importance of calculated slopes and high-lipped containers. Food selection influences logistics. Over 90% of terrestrial animals are herbivores or frugivores, which simplifies the baseline diet. For carnivores, viable paths include dried fish or cured meat in small portions, use of natural mortality, inevitable in a large population, torpor, inactivity, reducing appetite to minimal levels. There are omnivorous species with dietary plasticity, think bears or canids, capable of eating plants and insects when meat is scarce. In emergency confinement, less varied but nutritionally sufficient diets can sustain for long periods. Day to day, the operation demands a strict routine. 1. Refill sector bins, avoiding long manual hauls. 2. Trigger gravity by wings, shot aisles, minimizing turmoil. 3. Check drinkers and close gates. 4. Remove waste with shovels and trays. 5. Inspect stalls, doors, and locks. Cleaning is the link that keeps the system healthy. Where there's food, there will be waste. The plan calls for slightly sloped floors, side drains or gutters, and trays under raised stalls. Mixing excrement with straw, shavings, and ash favors composting, a process that generates heat, reduces odor, and inactivates some microorganisms. Periodically, the material follows disposal routes that don't cross feeding areas. None of this works if stress rises. Stressed animals eat poorly, fight, and get sick. Therefore, logistics marries behavior. Fixed schedules, low light in rest areas, visual barriers between predators and prey, and operational silence during feeding. Torpor induced by routine and stable environment helps save inputs. Another concern is mass balance. As stocks are consumed, the ARK's center of gravity shifts. The plan includes relocating bales among stores to keep the vessel level and avoid dangerous lists. Floor markings, tie points, and reference weights, lever scales, allow regular adjustments. Crew safety, corridors wide enough for two-way passage, doors that don't jam even with swelling, low-rise stairs for carrying loads, and redundant escape routes. Every detail saves minutes, and in confinement, minutes save lives. Robust simplicity. No motors or sensors. Gravity, wood, rope, bitumen, and discipline. The ARK operates as a passive circuit. Food descends, water flows, air circulates, waste leaves via slope and collection. Resilient systems exclude what can fail and duplicate what must not stop. Modern trials and analogies indicate, with planning and routine, it works for months. The secret isn't magic, it's process. Feeding isn't just filling troughs, it's governing a closed ecosystem. Store, distribute, clean, while keeping people and animals healthy and the hull stable. Sanitation is a pillar, not a detail. Without a plan, ammonia, methane, CO2, humidity, and pathogens would bring everything down in weeks. And yet, they survived. The answer? Passive engineering that exploits gravity, slope, capillarity, simple materials, and disciplined routine. Pillars. 1. Floors with gentle fall and directed drainage. Carved or assembled gutters conduct liquids to cisterns or protected outlets. Flow speed matters less than constant direction, always away from living areas. 2. Raised stalls with grates and trays. Solids and liquids fall by gravity into removable trays, reducing contact, odor, and microbes. The same principle used in modern facilities. 3. Manual collection and composting. Service routes don't cross feeding paths. Feces plus straw, shavings, or ash in layers generate heat, dry out, inactivate some microbes, and become absorbent for wet areas or bedding cover. Even substrate for emergency cultivation. Gases under control. Bitumen in strategic points seals joints, contains odors, and isolates vapors. Tanks, gutters, waste compartments. Controlled ventilation, next topic, dilutes and expels the remainder. Sanitation plus ventilation form a coupled system. Nothing is improvised with rain pouring. Slopes, inspection hatches, cabinets, routes, and storage volumes must be defined beforehand. Flow separation, where food, water, people pass, waste does not. One-way corridors, outward opening doors, floor markings, and alternating cleaning windows and feeding windows prevent crossings. In sensitive stalls, collection happens right after feeding. Dirty water and human safety. Part is absorbed by dry bedding, straw, sawdust. The excess goes to internal soakaways. Rudimentary filters, pebbles, sand, charcoal, cloth, clarify for non-potable use, washing utensils. An effluent network isolated from drinkers. Cleaning progresses from the most ventilated sector to the least, with upper openings half open between cycles. Moistened cloth masks, gloves, and poles to pull trays reduce exposure. Operational resilience. The system must run on a bad day. If someone gets sick, if load increases, if a door swells. So gravity is prioritized over pumping, sloped planes over wheels, seals over valves, trays over drums. Fewer failure points, more reliability. Ethology aiding sanitation. Predictable environments, darkness in resting areas, visual barriers, and stable routine reduce stress, thus less diarrhea and urination. Demarcated elimination zones, with already used shavings, induce a specific corner, easing collection. Maintenance closes the loop. Gutters can clog with vegetal fibers, trays can crack, joints can open with wood expansion. A daily inspection checklist: look at gutters, feel seals, listen for creaks that reveal looseness, prevents accidents. Quick repairs with wedges, rope work, and bitumen maintain efficiency without relying on rare hardware. By the end of months, accumulated compost may reach significant volume. Instead of becoming a problem, it becomes a resource. It serves as an acoustic barrier around sensitive areas, acts as ballast to rebalance the center of gravity as food stocks shrink, and can absorb splashes in corridors. Nothing is wasted. Everything re-enters the system with purpose. Finally, it's worth underscoring the principle running through the ARK's sanitation: anticipation. The project doesn't arise from reactions, but from questions asked beforehand. Where does the water escape? Where do solids fall? Where do gases go? Who cleans, and along which route? When answers become sloped wood, well-placed doors, and exclusive pathways, the ARK stops being a mere symbol and becomes a rudimentary, efficient, sustainable ecological system. Had this knot not been untied, everything else would have collapsed. The fact that it didn't suggest sanitation was indeed planned. And it's precisely here that the theme connects to the next. Without fresh air and thermal control, no sanitation is enough. The mechanism only closes when the environment breathes. If you enjoy the intersection of science and faith, drop a like and come along. What comes now is the ARK's invisible heart: ventilation. Breathing seems simple until you put thousands of organisms in a wooden enclosure, without motors, mechanical ducts, or electricity, for months. Keeping air renewed, dry enough, and thermally tolerable becomes the difference between a viable habitat and a trap. The biblical text mentions a minimal yet decisive instruction. You shall make an opening, zohar, and finish it to a cubit from the top. A short sentence that embeds a complete concept of passive ventilation. The term zohar is translated as window, skylight, or light. Some understand it as a continuous slit running near the ceiling. Others as a set of vents with movable flaps. In both cases, position is what matters. High enough to exhaust hot air and light gases, protected enough not to admit water, even under rain and wave spray. How does that solve a volume on the order of hundreds of thousands of liters of air? With the most reliable force in sealed environments, the stack effect. Animals and humans constantly produce heat. Warm air rises and seeks an escape. As it leaves through the upper opening, it creates negative pressure that pulls in cooler, oxygen-richer air through lower gaps and vents. No fans, no cables, just convection. The stack effect also regulates temperature. In crowded spaces, CO2 and water vapor rise with warm air, and the opening above expels that package. The result is a gradient. Fresher air enters low, used air exits high. It's the same principle in bioclimatic buildings and traditional kilns, applied to an ARK. Three-dimensional models suggest that a longitudinal slit, about a handspan wide, 45 centimeters, along the top would suffice to promote continuous renewal under moderate wind and with metabolic heat as the driver. On heavy rain days, wooden flaps or vegetal screens deflect water without fully sealing airflow. Think of modern ship vents. Allow air out without letting water in. Ventilation also impacts humidity control. Condensation on wood fosters fungus, mold, and warping. With an upper vent, humidity rises and exits. With lower inlets well placed, gaps, door clearances, side vents, a current is formed that sweeps corridors and stalls, drying bedding, straw, shavings, faster, and reducing odors. And the light? The zohar isn't just for ventilation. It's a safe source of diffuse illumination. In long confinement, circadian rhythms matter. Constant darkness induces apathy, disorganized lethargy, and aggression in many species. Natural light, even indirect, organizes cycles of rest, intake, and wakefulness. Without open flame, fire
is
risk,
typically
the
translated
skylight
as
is a double
window or
solution:
skylight.
air and light. To avoid turning the opening into a structural weakness, the design uses raised eaves, combings, and covers that overlap the slit like an inverted roof. Water flows outward. Air escapes through lateral gaps. In rough seas, this geometry breaks spray jets and dissipates energy, preventing infiltration. Respiratory safety for sensitive species, birds and small mammals, for instance, benefits from proximity to the tsohar, upper level. Large herbivores below benefit from air descending along the sides and renewed by stack effect. In carnivore stalls, barriers and doors with high vents maintain flow with less sound and visual disturbance. Ventilation dovetails with sanitation. Removing waste without renewing air doesn't solve the problem. Hence, cleaning routines occur with the tsohar open, preferably when external temperature increases the differential with the interior, boosting thermal draft. In very cold days, partial closures reduce heat loss without stopping exhaust. There's also the dynamic of impacts and spray. The top must withstand debris strikes and wave blows. Therefore, tsohar covers aren't flimsy. They're thick boards set at angle, with cross members that transfer load to the roof's framing. Even if part of the slit must close temporarily, the system provides alternate openings along the length to keep minimum flow. The general logic can be summarized in 4 verbs: heat, rise, exit, replenish. Heat. Biological heat generates buoyancy. Rise. Used air rises by density difference. Exit. The tsohar provides a route. Replenish. Lower inlets supply fresh air. This mechanism doesn't break, heat doesn't run out of energy, and gravity doesn't fail. It's the right choice when reliability is non-negotiable. From the human standpoint, ventilation helps preserve sanity. Less stuffy corridors, tolerable smells, and sufficient light reduce fatigue and improve morale. Critical ingredients in prolonged isolation. In submarine and space installations, the oxygen temperature light triad is treated as vital. The ARK anticipates that reasoning with minimal resources. Modulation remains. You don't always want the same flow. In cold days, heat losses must be controlled. In hot, humid days, exhaust must be increased. Hence, curtains, louvers, and adjustable hatches. The family regulates the system by hand, sector by sector, opening more where there's odor, closing a bit where there are young or debilitated animals. Finally, integration. Ventilation isn't an extra, it's structure. The 3 decks act as diaphragms that stiffen the hull and, at the same time, create air shafts and corridors. The layout of stalls and passages is planned not to block airflow. Tall clearances in panels, drains that also draw cool air, stairs that don't touch the ceiling, allowing hot flow to slide. In conclusion, the ARK's greatest challenge wasn't to float. It was to keep life stable inside. And life is only sustained when the environment breathes. The tsohar, simple in form, profound in effect, is the piece that ties sanitation, thermal comfort, humidity control, and biological cycles into one design gesture. That's what turns a wooden box into a functional habitat. Without this window that doesn't let water in, everything else would have been insufficient. With it, the impossible becomes measurable, and the ARK habitable. Nothing prepared those 8 people for what came next. Raising the ARK was one journey, living inside it, another. But enduring the chaos, that was the real test. The beginning of the flood was anything but gentle. The text is direct. all the fountains of the great deep burst forth, and the windows of heaven were opened. In other words, water from above and below at the same time. A seismic, hydrological, planetary event. At the center of that fury, a box floating. No rudder, no sails, no directional keel. Noah didn't steer. He trusted. But would that be enough? Current research simulates extreme seas, wave tanks, computational models, scale prototypes. When they test different shapes, the result is consistent. The long, broad, flat-bottom geometry isn't efficient for speed, but it's exceptionally stable in vertical motion. Instead of cutting the wave and risking a capsize, a wide rectangular form behaves like a barge, damping impacts and avoiding full rolls. Engineers call it passive stability. Comparative studies, with various profiles of ancient vessels, point to the 6.1 proportion, length-width, attributed to the biblical design as one of the best for reducing the risk of capsizing on the open sea. Even without active control, such a structure turns with the current, keeps the center of gravity low, and protects its contents. But the challenge wasn't only hydrodynamic. It was 370 days, practically a year, without seeing land, without a firm horizon, with the constant sound of working wood, a restless bestiary, and water pounding. Absolute isolation, repeated routine, silence broken by crashes. Those who study prolonged confinement, astronauts, polar researchers, submarine crews, know mental health weighs as much as food and shelter. The ARK, unintentionally, became the first lab of human coexistence in a capsule. And yet, they endured. Why? Psychologists list 4 pillars. 1. Daily structure: feeding, cleaning, checking, repairing. The cadence of care fills time, gives a sense of progress, and keeps the mind occupied. 2. Non-negotiable purpose. The mission to preserve life gives meaning to discomfort. Suffering with meaning is more bearable than discomfort without horizon. 3. Family unity. In tight space, collaboration reduces friction. Distributed tasks, practical decisions, less energy spent on conflict. 4. Future hope. Each extra day isn't more of the same. It's a day closer to the end of judgment and the restart. Even so, there was fear, fatigue, uncertainty. The storms weren't brief. It rained 40 days and nights, but waters took over a year to recede. In that interval, the ARK faced repeated waves, logs and debris colliding, peaks hidden beneath the waterline. Why didn't it break? Because the interior functioned like a skeleton. The 3 decks acted as structural diaphragms, tying the walls. Bitumen sealed cracks and absorbed micro-vibrations. The wood, elastic enough, yielded without breaking. The design anticipated the unpredictable. The ARK wasn't conceived to navigate. It was created to survive. That paradigm today inspires tsunami refuges, floating houses, emergency capsules, low center of gravity, passive stability as a priority, few moving parts, fewer failure points, resilient materials, strong yet capable of elastic deformation. The ARK had all of this. It was at once a capsule, a storehouse of hope, a testament of endurance, till one day the motion ceased. The rain fell silent. The waves rested. Silence returned. And this time, it brought relief. After 370 days over a world covered in water, the ARK touched land. Not by plotted course, but by mission accomplished. When the door opened and each being went out, history began again. From the vantage of engineering and psychology, one synthesis remains. Resisting chaos requires structure, prudent design, and meaning. Without these three, no box floats that long. With them, even the impossible starts operating within measurable bounds. And perhaps that's the point. The impossible didn't cease to be. It merely gained foundations. The waters withdrew. The clouds opened. And, for the first time in over a year, the sun warmed dry wood. The Ark fulfilled what it was made for. An improbable structure, raised in an illogical place by common people, withstood what no ancient civilization would dare design to face. But the legacy wasn't locked between planks and bitumen. The true legacy is what the Ark delivered to the future.
Father,
Today,
did the
from naval
dinosaurs go
laboratories to
too?
research groups, from science museums to universities, its measurements, materials, and internal logic are analyzed with technical eyes. And piece by piece, the conclusion isn't sensational, but powerful. It is possible. The project makes sense for what it proposes, not to navigate, but to preserve. Beyond the math, there's something formulas can't hold. Vision. The Ark is wood, yes, but it's also forethought, converted into a plan. A drawing moved by something technique doesn't deny, only doesn't measure. Faith. Tools without conviction don't build for decades. Strength without purpose doesn't weather storms. Noah had both. He calculated with what he had, and waited with what he believed. In a world facing new storms, climatic, social, personal, the Ark reminds us of a simple principle. You can't always prevent chaos, but you can always prepare to resist it. We can build without seeing the ocean. We can plan before the clouds gather. We can trust even without complete guarantees. Sometimes, the work that saves isn't what shows on the outside, but what holds from within. A reinforced hull, a committed family, a promise anchoring the weight. Perhaps the Ark still sails, not on waters, but on the memory of those who choose to believe before the first drop. If you also believe knowledge and faith can walk side by side, leave your like, subscribe, and come discover other secrets hidden in the pages of the Bible, where ancient stories keep opening new projects for our time.